Hi, welcome to Module 3, and in Module 3 we would be exploring Ethereum core concepts. So let's start with what Ethereum is. Ethereum basically is a decentralized open source blockchain platform that is designed to run smart contracts and decentralized applications across a network of computers or nodes. And unlike Bitcoin, the Ethereum blockchain can store and execute arbitrary code, which enables a rich ecosystem of applications on chain. So in Module 3, we'll basically be exploring the fundamental architecture of Ethereum, the Ethereum virtual machine, smart contracts, and the broader Ethereum ecosystem, including scaling options and layer 2 technologies. So what forms the Ethereum architecture? We have the peer-to-peer network. By now we are not new to what peer-to-peer network is basically all about anymore. So the Ethereum operates as a decentralized network of nodes, which means that each node runs a full copy of the blockchain. And the benefit of this is that it enhances resilience, security, and also censorship resistance. And the global state of all accounts are maintained by each node and updated with each new block that is added to the data structure, which makes up the world state. And also, the blockchain, as we all know, is a chain of block that contains transaction data, metadata, and links to previous blocks that creates an immutable record of all network activity. So we have two types of Ethereum accounts. We have the EOAs and then we have the contract accounts. So the EOAs are basically controlled by private keys and they grant ownership and control over Ether and smart contracts. And this is similar to a traditional bank account but with cryptographic security. So some of the benefits are that you can basically track your Ether balance and there are no associated code with EOAs. This can be used to initiate or sign transactions and it is controlled by private key. Whereas for the contract accounts, these are created and managed by smart contracts, which also hold Ether and basically execute code based on specific triggers. And like software applications, they have their own logic and data storage. So this has code, and like we know, these codes can be triggered or they execute when certain conditions are met. And these contract accounts can also interact with other contracts. So we have the EVM. The EVM is a virtual computer that executes smart contract code on every node. And it does this by isolating the contract execution from the host machine. Each contract or each execution on the smart contract by the EVM has a gas cost, and whoever is interacting with the smart contract or the EVM must provide enough gas to cover this execution, whether it be deploying or interacting with the smart contract. So we have gas, which is basically the mechanism for metering computational effort. Like we've just said, gas must actually be provided to whether you're interacting or you're deploying to the blockchain network. Then we also have persistent key value storage for contracts. And we have opcodes, which are low level instructions that are understood by the EVM, such like machine language. And then we have the runtime environment that executes smart contract code on every node. So we come to smart contracts. What are smart contracts? Smart contracts basically are a collection of code or functions and data that resides at a specific address on the Ethereum blockchain, and these rules can be automatically enforced if certain conditions are met, right? So all of the agreement, all of the things that need to be done are implemented into the code and stored on the blockchain. So the characteristics of smart contracts include, but not limited to, self-executing when conditions are met. They are also immutable once they are deployed, which means that once they are deployed, no changes can be made to smart contracts. And they are also transparent and verifiable, and they can hold ETH and tokens. And the application of smart contracts include decentralized finance, NFTs, DAOs, and supply chain tracking. So these are basically not the only applications of smart contract, but these are some of the most popular applications of smart contracts. So we're going to talk about the transition from proof of stake or from proof of work to proof of stake in the Ethereum network. So Ethereum basically started with proof of work, which is a way by which miners expend energy to solve cryptographic puzzles by determining the previous hash so that they can add it to the block and then choose the next block. And this basically consumes significant electricity, and it was basically not good for the environment. But in September 15, 2022, there was a merge, and Ethereum merged its execution layer with the Beacon chain consensus layer and transitioned from proof of work to proof of stake. So Ethereum currently runs on proof of stake, and validators need a minimum of 32 ETH as collateral to propose and choose the blocks or add the new block, and this reduces energy consumption by 99.95% as against proof of work. So the Shanghai Capella upgrade in April 2023 enables stakers to withdraw their staked ETH, and this completes the core proof of stake functionality. So gas fees basically serve multiple purposes. They compensate validators for processing transactions. They also prioritize transactions during network congestion and also prevent abuse of the network resources. And these fees basically fluctuate based on demand. So when the network is basically very busy, the fees increase as users basically complete or compete for block space. But the EIP 1.9 update in 2021 of August revamped this mechanism to make pricing more predictable and introduced a deflationary aspect by burning of base fees. So we're basically going to be talking about why fees are burned and what are the advantages of burning and things like that. So we have gas unit measurement, and this measures computational work required for operation. Then we have the gas price, which is the amount of ETH paid by unit of gas in GUE. GUE is basically the lowest form of ETH. And then we have the EIP1 fee mechanism that we've basically talked about, where the base fee is burned, but the priority fee, which is the tip to the validators, remain with the validators basically. So what are some of the scalability challenges faced by Ethereum? Ethereum also faces the blockchain trilemma. We discussed this in the previous module. So it is basically very, very difficult to achieve decentralization, security, and scalability simultaneously. The base layer basically prioritizes security and decentralization. So this basically limits throughput. So when transaction demand exceeds capacity, users experience network congestion and slower confirmation and higher gas fees. So this is the problem with the scalability issues. So we have the layer 2 solution, and this is basically very, very important because a lot of popular networks out there are built on existing blockchain networks. So the reason why those are very, very popular is because they solve particular scaling solution. So layer 2 solution process transactions off the main Ethereum chain but they rely on Ethereum for security and settlement. So they process the bulk of the transactions off-chain, but use Ethereum for data availability or dispute resolution. And this increase throughput and reduce the cost. So for rollup, the batch transactions are done off-chain and then compressed into the Ethereum network. So this basically allows them to inherit security from the Ethereum network. We also have state channels that allows participants to transact off-chain and submit final results to the Ethereum. And for Validium, we use validity proof but store data off-chain for maximum throughput. And for the sidechain, these are independent blockchains that run parallel to Ethereum with their own consensus mechanisms. So these are different kind of scaling solutions that we have in the Ethereum ecosystem. And a more detailed analysis would be included in the LMS. So you'll get a better understanding of basically everything that we're talking about for this module on the LMS. So what are rollups? Rollups are the flagship Ethereum L2 strategy because they basically can do hundreds of transactions and then submit them to Ethereum in compressed form, and this improves throughput 100 times more without compromising on security. And both types of rollups basically inherit security from Ethereum, but they also differ on how they prove the transaction validity. So for the optimistic rollup, they basically have an assumption that all transactions are valid by default, and they use fraud proof to challenge invalid state transition. So the withdrawal delay is around 1 week. It requires lower computational requirements, and examples of these are Optimism and Arbitrum. And then we have the zero knowledge rollups. This basically creates cryptographic validity proofs that verify the correctness of off-chain transactions, and this is basically done almost instantly. It requires higher computational requirements, and examples of this include ZK Sync, StackNet, and the Polygon ZK EVM. So sharding is basically the future of on-chain scaling, and there are a couple of things that has to be done before sharding is complete and the scaling solution basically comes to an end, right? So sharding will basically split the Ethereum data and state into multiple partitions that operate in parallel. So what this means is that each validator would process transaction for specific shard, and this basically distributes the network load. So the current roadmap that we have up there focuses first on data sharding to support rollups rather than execution sharding. And when this is completely implemented and this sharding is combined with rollups, this would enable the Ethereum network to reach throughput on the order of over 100,000 transactions per second while maintaining decentralization and security. So this basically means that once this is done, once this is completed, the blockchain trilemma is over. So we have the merge. We've transitioned from proof of work to proof of stake. That has already been implemented. Then would need to incorporate proto-Dan sharding, which is the EIP for, and this would include data blobs for rollups. Then multiple data shards for massive data availability, which is the data sharding. And when all of this is done, the sharding is completed, and the blockchain trilemma is completely solved. So the Ethereum ecosystem is composed of a couple of things: the developer tools, wallets, and dApps. So we have software wallets like MetaMask, we have hardware wallets like Ledger, and also paper wallets that provide different security models for storing private keys and also accessing the Ethereum network. So without a wallet, you basically cannot access the Ethereum network or interact with it. We also have decentralized applications like Aave, Uniswap. We also have NFT marketplaces. We also have games that are basically have been built on the Ethereum ecosystem. And we also have developer tools. We are here to learn how to develop on the Ethereum network. So we'll definitely be learning Solidity programming language and development frameworks like Truffle, Hardhat, and would be using IDEs like Remix and block explorers like Etherscan. And all of these are required to basically be a blockchain developer and to build on the Ethereum network. So that's about that for module 3. A more detailed analysis is included in the LMS. So we look forward to discussing these things further in class. If you have any questions, do bring them to class and then we'll discuss further. So until next time.